It looks like we're all set and ready to record, so neat. So in any event, welcome back. In the next few sections, we're actually going to begin our deep dive into the N-True crypto system. So this fun little world is actually one of the finalists in the NIST post-quantum standardization process. So it becomes a pretty cool system that we get to begin pulling a bunch of the stuff that we've been working with, as well as seeing a few new goodies kind of all blend together to actually look at one of these, finalists that are actually going to hopefully become one of our official standardizations. So to get there, we actually need a little bit more of build-up / some introduction of a few new topics. So these topics are actually easiest to think about in the world of polynomials. So we're actually going to be living here for now, but the big thing to be thinking in the back of your head is that polynomials are not really fancy objects. They're just simply lists of all the coefficients. So when we begin doing operations on polynomials, we're really just doing some crazy list manipulation. So we're gonna kind of view it like all of our old school, middle school polynomial chat, but then we're going to slowly peel this back, begin viewing these things as lists, and then begin shoving them into some lattices, and then do all the fun lattice stuff that we've been running through already. So anyway, enough chat. Let's actually go ahead and introduce some notation so we can begin to see the meat of this whole process all come into focus. So the first thing that we're going to be introducing is going to be this notion of these polynomials that are going to have integer coefficients. So the notation for this is going to be this crazy little object down below. So it's the z for integers, and then it's going to have this bracket afterwards with an x inside of it. And that x inside of it is then going to tell me the variable that my polynomial is going to be made out of. So you can have polynomials with x variables or z variables or x and z variables or x, y, and z or any number of variables. So it's kind of this starting the process here of just I'm going to have where my coefficients are living from. So it's going to be in the integer world. And then I'm going to have my variable, which happens to be an x. Officially, this is part of a slightly larger world, which you can actually build polynomials out of any what are going to be referred to as rings. So later on, we're going to begin changing up what our coefficients are. So that notation is actually consistent. It's always just going to be wherever your coefficients happen to come from. So those are going to be your AIs. And then the bracket part is just going to be your variable you're actually working with. So the first and easiest one is obviously when your ring is just the integers. So we have this little polynomial f, which is 1 plus 3x plus 3x squared plus 7x cubed. So those coefficients of 1, 3, 3, 7 are all integers. That variable happens to be an x. So that polynomial is then going to live in this polynomial ring z bracket z. Whereas this other polynomial g, which is made up with 3.2 as my kind of initial little coefficient, what you can see there is that that's not an integer. So right from the get-go, I know that that thing does not live in z bracket x. It would live in, let's say, r bracket x if I allowed for real value coefficients. But here we're only allowing integers, so that one is out of the running, which is good. So we want to live with just nice integers as our coefficients, and then we're going to have some variables x. These little polynomial rings can have any degree you would ever want to see. So this one happens to be a degree 3 polynomial, though you could have a degree 30, you could have a degree 3 million, you could have any size degree you would ever want. For now, in a little bit, we're going to begin restricting the degree, which is, again, going to be that throwing back to that these really should be viewed as lists. And if I have degree 3 polynomials, then I'm going to have a list of 4 little coefficients, which are simply going to be 1, 3, 3, and 7. So having control over the degree is actually going to just be control over the size of this little list. So that's our first little ring that we're going to then be working with. And as I mentioned at the very beginning of this, is we can change where our coefficients are going to live in. So one of the things that we want to begin doing is viewing these coefficients modulo whatever prime we happen to want to work with. So that's going to be one little input variable that we're going to begin changing these things up. So kind of in the back of your head, be thinking like, there's going to be a crypto system made out of all of these things. So I'm going to have some degree information. I'm going to have some prime information. All of these extra little goodies are going to slowly come into these definitions down below. So the first of which is we can begin reducing those coefficients modulo whatever your favorite prime happens to be. So because these are all really small, I'm just reducing by some small primes just because otherwise it wouldn't change at all. So if I looked at this polynomial f, so 1 plus 3x plus 3x squared plus 7x cubed, if I reduced all of those coefficients modulo 3, well, the 1 wouldn't change because it's already reduced. The 3 would become a 0. The other 3 would also become a 0. And the 7 would then actually become a 1. So that thing would reduce down into 1 plus 0x plus 0x squared plus 1x cubed, which we typically would write just as 1 plus x cubed. But again, realize that that really is going to be a list of 1, 0, 0, 1. So it's kind of nice to play around with that a little bit. If you wanted to even push that a bit further, you could actually reduce that original polynomial, let's say with coefficients modulo 2. So here you're going to get a really nice little binary vector because all of those little weights are either going to be zeros and ones. So if I took 1, 3, 3, 7 and reduce all of those modulo 2, well, they're all odd. So it's all going to kick out ones. So you get this kind of fun little polynomial of 1 plus x squared plus an x cubed, which again, as a vector, would just be the vector of all ones. And you can do whatever you want to with that thing afterwards. So the original ring is going to be this thing. So this z bracket x. If I want to begin viewing those coefficients modulo some prime, what we do is we change the z into the z mod pz. So we're going to begin telling people what those things are going to be reduced by. So if I want to, I can introduce this new notation, which is the exact same thing as this one up above. I'm just replacing the r with a z originally, and now I'm replacing that r with a z mod pz. So what this is going to give me is it's going to give me polynomials with any type of degree that I would ever want, where the coefficients are then going to be viewed modulo p, whatever prime we happen to be working with. So you can begin kind of thinking about all of these crazy mixing operations that we're going to have. Well, they're all going to basically be inflated quite a bit because before we might have done work on, singleton components or singleton numbers. Now we're going to be doing things on polynomials. So we're going to have lots of freedom in terms of all of these coefficients that we can actually begin playing with. So there's a little bit of early on notation to kind of get this ball rolling. The next ball that we need to begin rolling is actually going to be some notion of inverses because it's a crypto class afterwards. And in order to do anything meaningful in any of these worlds, we're going to need to know how to do some type of inverse operation, which usually involves some type of Euclidean algorithm and extended Euclidean algorithm. Lucky for us, we can actually do that in the world of polynomials, and that's actually what we're going to be doing in the next video. So stay tuned for the extra goodies.